I'm glad you guys are here. I thought, well, I guess there's a few people. I guess we're only at, what, 5 right now? Jeez. But I was actually expecting fewer because it's the day before Thanksgiving. But this has been an action-packed week. Oh, man. I'm beat. I've had 2 sets of meetings before each class. I didn't even get to eat lunch. Except for M&Ms.
Yeah. Trust the M&Ms.
Yeah, M&Ms. And no one likes the 100 grands. It's like, these are the last sets of M&Ms. The only thing I got left are 100 grands in the candy. I'll get fresh candy for you guys. Anybody have any requests? It's whatever they sell at Costco, though.
Yeah, all good.
Do you want something non-chocolate? Well, I guess chocolate's supposed to help with test anxiety, so I guess I'll have to find chocolate.
Yeah. Thanks for looking out for us.
Yeah, no worries. Okay. All right, so I guess I gotta start. It's noon. So, last class before Thanksgiving. Okay, as much as I hate saying today, also some of the stuff we're gonna talk about today is applicable, but much of it is essentially flawed, and we'll talk about that. I don't know if we'll get to it this class. This depends on how much time we go through. We might be able to get to it, but we'll talk about how things really work. And although this is true, this diagram is true. And right now what we're talking about is why things bond. And how we thought things used to bond. And why are we talking about this? And, because it's important for organic chemistry. So this theory, although incorrect, is still used in organic chemistry. But this red line is true. So this red line is true. The graph is true, but the idea behind it. So how things bond. So the idea is that you have 2 atoms, so in this case hydrogen. So this 0 line, this is 2 hydrogen atoms infinitely far apart. Now as the hydrogen atoms approach each other, what happens is they start to share electrons. And as they get closer, they start to, they have this point where it's the maximum. So that's where they have the ideal overlapping of electron clouds. So in this picture, you can see you have the internuclear distance getting bigger, and you get to a point where you have a maximum bond, a minimum in potential energy. So anyways, let me, the y-axis on this graph is potential energy. The x-axis is the distance between the hydrogen nuclei. And as 2 hydrogen atoms approach each other, they get closer, the potential energy goes down. And that's the reason why things bond, is because the energy level, the overall energy goes down. And there gets to a point, though, where they, after this idealized bond length, they get closer, what happens is the nuclei, so the nuclei are positive, they start to repel, and then the potential energy increases. And then they get to a point where they're so close that they'd rather be apart than bonding anything at all. So this is kind of like if you're ever flirting with someone. So the classic way to flirt with someone is to get closer to that person. So if you're interested in someone, like, you know what, maybe take a step towards that person when you talk to that person. But there's a happy medium, right? So if you're like, I like you, I really like you, and you're like walking away, that's, indicating that you don't like that person. But if you walk towards someone like, oh, I like you, hi, so glad to talk to you, kind of thing. But then again, there's a comfortable distance. What happens when someone gets too close to you? You're like, man, you're right in my face. I don't like this. Then there's the repulsion factor. So atoms work the same way. Atoms, molecules work the same way. If they're too far apart, they can't bond. They're close enough, they can bond. And there's this optimal distance. Like I like you, I like this. You're here, you're over here. We're close enough, we can hold hands. This is good. Nope, oh, now you're in my face. I don't like it when you're in my face. You're too close. I'm repelled by you. That's this case. The electron clouds get too close together, and then the nuclei start to repel. They're both positively charged. The potential goes up. So this chart is true, actually, and this is also known as the Leonard-Jones 612 potential because the equation, the governing it is to the 6th power to the 12th power. So there's actually a love story behind him. Leonard-Jones, he married his wife, and then he took on her name as well. So rather than so he went from Leonard from Leonard to Leonard-Jones. So he hyphenated it and took his wife's name as well. So back in the day, that was not very common. So, but okay, so. But this is also saying, okay, how do atoms bond? They can bond by overlapping electron clouds. They don't, but we're trying to explain it. And then if you look at orbitals, so let's think of the molecule hydrogen sulfide, H2S. And if you look at the atomic orbitals, so sulfur has p orbitals and hydrogen has s orbitals. The p orbitals are perpendicular to each other. P does not mean perpendicular, it means principal. But the p orbitals are perpendicular to each other and they can overlap that way. With this theory, it would suggest that the bond angle would be 90 degrees when it turns out that it's not 90 degrees. So it's actually it's a tetrahedral. It's 109.5 degrees, a little less than that with the valence shell repulsion. So what happens though is that the orbitals hybridize. So the idea is that a hybridization of the orbitals takes place. So for the tetrahedral electronic geometry, the hybridization is sp3. So the idea is that the s orbitals and the 3p orbitals of the atom form 4, so 1, 2, 3, 4. These 4 atomic orbitals hybridize and form sp3 hybridized orbitals. And the shape of these is as such, as tetrahedral. So here's the s, here's the p's, and they hybridize, so they form orbitals like this. So the s is a sphere. There's the p's here, and the p here. They hybridize to form an orbital here, a small one here, one here, and then same thing down there and down there. So it forms a tetrahedron. Is this really what happens? Geometry-wise, it's true. What really happens is when two atoms approach each other, new orbitals will form. Those are called molecular orbitals. We'll talk about that later. But this theory works almost every single time, and it's even taught in organic chemistry. I'm sure you guys talk about hybridization in the orbitals, right? Yeah. So, okay. So now this is explained. Okay, well this is that the bond overlap. The idea is that the hydrogens and then bond there with the carbon. So what about for double bonds? So you can also with carbon having a tetrahedron. What about planar geometry? So we're going down. Instead of sp3, it's sp2. So there forms 3 sp2 hybrid orbitals and then the unbonded p orbital. And in the case for sp2, it forms 3 sp. So 1s, 2 p's form 3 sp2 orbitals, and it forms a planar geometry. So if you look at this molecule here, so this is formaldehyde, and the bonding in formaldehyde. Yeah, you can see that. So carbon and oxygen here, and the carbon has the sp3 hybridized orbitals. So I'm sorry, sp2. Sorry, sp2. So then there's an overlap. Oxygen also is going to form an sp2 because it has two low. Or I guess this one shows no. It should be sp2 because it has 11 pairs. But the idea, though, is that the p orbital, or the sp2 orbital, is overlapping here, and then there's the bond here between the carbon and the hydrogen. And this is all coplanar, so this is a flat molecule. Now let's talk about the different, and then the double bond, there is a double bond above and below. So let me explain that. So a single bond, all single bonds are known as sigma bonds. So if you look at my heart and my fist, the sigma bond means that the bond is along the internuclear axis. The internuclear axis between my heart and my fist is my arm, right? So this here, this is the sigma bond. So it's along the internuclear axis between the two nuclei. So then a double bond is a sigma bond, so one sigma bond, and then a pi bond. The pi bond is above and below the internuclear axis. So here's a sigma bond, the pi bond is here. And it's because, so for like a carbon and oxygen, there's a p orbital here, and over here there's a p orbital here, and then they overlap above and below. So that actually, I keep on going back to saying, oh, this is right, but now let me tell you what really happens. What really happens is the molecular orbital forms. It does, in fact, go above and below. So molecular orbital theory and valence bond theory say the same thing, that there is a new orbital formed. And so this is important for a few reasons. So for single bonds, so if you have a single bond, it can move. So sigma bonds, it's real easy to move. If it's like a methyl group, a CH3 group. I left my water bottle is empty. I should have, I can use a cleaning solution. So if you have a bond with another group on it, it can move freely. So you can get things moving along a sigma bond only. If there's a pi bond, if you rotate it, you have to break the pi bond, because the pi bond is over there overlapping, so it's really hard to rotate things with a double and or triple bond. So, okay, so that makes sense. We're defining different types of bond. Sigma bond along internuclear axes, and then a pi bond is above and below. So you can have, and by 3 dimensions, you can have a pi bond here, and you can have a pi bond here. So there's one pi bond there. So a sigma bond parallel the internuclear axis, I said alongside, and a pi bond above and below. Internuclear means between the nuclei. And I just mentioned this free rotation. So you have ethane, you don't have to worry about the name, but ethane, 2 carbons, 2 CH3s. So ethane, the bond is really just kind of flows around. It twists, it turns, it moves around. Ethylene, this is 1,2-dichloroethane. This is 1,2-cis-dichloroethene, and this one does not have free rotation. It's fixed. And we talked about cis and trans last class. So, and the other thing is that the way that the molecules situate themselves. So, now these 2 molecules here are shown on the diagram. This is showing it with the kind of ball and stick model more. You can see the balls. So and what happens typically, although there's free rotation, the chlorine's a big atom. It has a big electron cloud. So what the chlorine does is the molecule twists and turns so the chlorine atoms are as far away from each other as possible. And actually, this has a name. It's called the gauche form. That might be a German word. I don't know. It situates itself so it's far away because, remember, electrons, they're big clouds and they are negatively charged or repelled. So the molecule situates itself so the negative groups are as far away from each other as possible. And but although at a temperature, because so temperature, average kinetic energy, it still moves around. It kind of stays away from each other, but it's still free to move around. It'll start to look, oh, that's too close, move back. Oh, then repels back here. It still moves around at a reasonable temperature. So I mean, if it's absolute zero, at absolute zero, it's going to be like this and not move. Well, it'll move, but it'll vibrate and rotate, but it won't really move all that much, except internally. But it'll stick here like this. If it's a higher temperature, it's going to move around. But then you get to a double bond where you have cis and trans. With this double bond, it's fixed. It's not going to move. So trans is lower energy than cis because trans along a double bond, these are far away. Cis, these are close. Lower energy is trans, and that's why we talked about with the trans fatty acids and margarine. So trans is actually slightly favored over cis. But in biological things, we don't know why, but biological things, all the acids are all cis. But okay, so can you break this bond? Yes, you can. Needs energy. So you can switch between cis and trans, but there needs to be energy, something like temperature or a photon, and that is how our eyes work. So, and our rods and cones work in part using the molecule retinal. So, retinas are eyes, our light-sensitive cells in the back of our eyes are called our retina. And also vitamin A is called retinol, right? So if you don't get enough vitamin A, retinol, you get night blindness. So the molecule retinal, it starts out as cis, and when it gets hit with a photon, it'll change to trans. And then this is how we can send our signals to, that's in part how the light signal is sent to our brains. Is from this switching event, but it takes energy to break the double bond. Okay, how are we doing for so questions? Everyone's good. Okay. Everyone looks so attentive. And I mentioned this we're doing the Vesper theory chart. Oh, we didn't talk about, I'm sorry, let me talk about linear. I haven't talked about linear yet. So for linear geometry, the s and a p orbital can combine to form two sp orbitals, as I've written there in yellow. And so if you look at the bonding scheme for a triple bond, so for a triple bond, it's going to be, so if you look at a molecule like acetylene, so acetylene, or the formal name ethyne, so this molecule works by, you have a carbon attached to a carbon, to a hydrogen, and has, the carbons are going to have the sp orbitals. There's two of them. There's going to be an overlap here with that. There's an overlap here for the hydrogens. So you have a sigma bond there, a sigma bond there, and a sigma bond there. And then the carbon is going to have a p orbital, so perpendicular to the, or up and down with the y-axis in the plane. and then here sticking out too, there's another p orbital. And then they overlap. I should use they'll overlap alongside these p orbitals here and here like that. So that's a triple bond. A triple bond is 1 sigma and 2 pi bonds. So let me explain this using miming, or maybe spoken miming, I should say. So we have a carbon and another carbon. So what the carbons do is they form sp hybridization. So one of the s orbital and one of the p's. So there's 3 p's, right? There's the p here, and then the p here. The p's along here with the s orbital will form an sp orbital and an sp orbital. So this one will bond to a hydrogen, and then this one will bond to a carbon. So then you have a sigma bond here and a sigma bond here between the hydrogen, carbon, and the other carbon. And then there's open p orbitals here. The other one has an open p orbital here, and then there's one here, and there's one here. So the overlap's going to be here and here for a pi bond, here and here for another pi bond, for in 3 dimensions. So does that make sense? And then the overall scheme is for linear electronic geometry. The hybridization is sp. For planar, it's sp2. For tetrahedral, sp3. Now for the bipyramid and octahedral, so remember the expanded octets can only work for period 3 and above. Why period 3 and above? Because there's d orbitals, and then it can form the sp3d and then the sp3d2 for the octahedral. So bipyramid, sp3d, octahedral, sp3d2. And if you remember, I talked about that when we had the chart. I went ahead and put that in there. So this is where I told you it would become important later. So now is when it became important. So what is the hybridization and bonding scheme for ethene? So ethene, also known as ethylene. So ethylene. So to me, the smell of ethylene, it smells kind of like rotten bananas. There's ethylene is a molecule. You might be aware of the plastic called polyethylene. So this is high-density polyethylene. It's almost all the plastics are high-density polyethylene. There's also, so your desktops, I think these, yeah. Yeah, that's actually vinyl. So your desktops are polyvinyl chloride, sometimes just referred to as vinyl. So used to make records out of them, so vinyl records. But most plastics that we have are polyethylene. So HDPE, high-density polyethylene. There's LDPE, so low-density polyethylene. That's what like milk jugs and plastic bags at the grocery store. I mean, they're banned in Hawaii now, but they're made of low density. So, okay. But also ethylene, it's known as something that's autocatalytic. So maybe you've heard the old saying, like a bad apple will spoil the whole bunch. Have you heard that one before? So fruit, when it ripens, it releases ethylene, or ethene. Ethylene is the common name. Like water is a common name for dihydrogen monoxide. So ethylene is released when fruit is ripened, and ethylene causes fruit to ripen. So if you take a rotten piece of fruit and put it with fresh fruit, it'll make the fresh fruit ripen faster. Also, if you notice, like if you want avocados, I like avocados. If you want an avocado to ripen faster, what do? You put it in a bag. So if you put it in a bag, it'll ripen faster. And have you ever gotten some fruit? Sometimes they treat fruit with ethylene. So you ever gotten a banana? It's like nice and yellow, and then you break it open, and you're like, oh man, it's not ripe yet on the inside. Just throwing ethylene in things, it can ripen the outside, and that's a trick that people can do for food. We do this a lot for food. You treat meat and fish with carbon monoxide as well to change the color. So you didn't know that? Or if you look at poke, if you go to Foodland and buy poke, it'll say treated with carbon monoxide. Gives it a different color, which is more.
What color?
a pinkish color.
Oh, it makes it more pink
Yeah.
rather than brown.
Yep, brown or purple, it's more pink.
Hmm.
Same thing with meat. They treat meat with carbon monoxide to make it look better. It doesn't, when you eat it, doesn't matter. It's the same thing. It's just one of the tricks. So, but, oh, and maybe you've noticed this if you, like I like to buy big things at Costco. So I'm almost through my big bag of carrots from Costco. But if I let it sit too long, if I smell carrots, it'll smell like bananas. Like, well, not, banana has a specific flavor smell to it, but you can smell the rottenness. That's the ethylene. So you might notice that rotten fruit kind of has a smell. I mean, there's other smells because there's other flavors inside the fruit, but there's this kind of baseline smell for rotten fruit you might notice. You're smelling the ethylene. And I used to live on Oahu for 11 years. There's this place called the Health Bar. It's on, it's right by, you're familiar with it. Yeah, it's right by Capilani Community College. And they like to make banana bread. They leave a bunch of bananas on their front. And you walk in that place, it's like a smack across the face with the ethylene smell. Have you noticed that? Yeah, you walk in there, you're like, whoo, right? Like rotten bananas, but I'm like, ooh, ethylene. You know, so if you know the proper smell. Okay, so that's ethylene. And the bond scheme here, so it's the Lewis structure. I should draw the Lewis structure. Lewis structure for it is this.
So that's what you smell when someone's putting off ketones, ethylene glycol.
Ethylene glycol is antifreeze. That's something different.
Okay.
Ketone is a different molecule. Ketone is a carbon chain with a double bond O in it that's not on the end.
Okay.
So ketone is also from ketosis or ketoacidosis.
Mm-hmm.
That's when not a lot of carbohydrates are in someone's diet. So there's that's a different field entirely. So ethylene is known as an alkene. It has a double bond. But that's organic chemistry. That's beyond the scope of this class. Okay. So carbon-carbon double bond with two hydrogens on each carbon. So which means the carbon with three things, it's planar, which three things means sp2 hybridization. So it's sp2 as such. And then the carbon atoms are going to have a single sigma bond between them. The hydrogen atoms have a sigma bond with a carbon, but the two carbon atoms will also have a pi bond between them. So here's one carbon, two hydrogens, and then a sigma bond to the other carbon, and the other carbon has two sigma bonds here, then a sigma bond with that carbon, but then again there's this open p orbital, so there's a pi bond between the two carbons as well. So in this molecule, there are 5 sigma bonds, 1, 2, 3, 4, 5 sigma, and then 1 pi bond here. So, make sense? And in general, so a single bond is a sigma bond. A sigma bond means along the internuclear axis. A double bond means 1 sigma bond and 1 pi bond. And a triple bond means 1 sigma bond and 2 pi bonds. Generally speaking, it's not always true, but generally speaking, sigma bonds are stronger than pi bonds. There are some cases where you have pi bonds that are stronger than sigma bonds, but that's not usually the case. Usually speaking, sigma bonds tend to be stronger. What I mean by stronger, it takes more energy to break them. Okay, let's see if you're following. So let's talk about, so remember hybridization, linear geometry, SP, planar, SP2, tetrahedral, SP3, bipyramidal, SP3D, octahedral, SP3D2. So what is the hybridization of sulfur and sulfur hexafluoride, SF6? So how many things are around sulfur? So there's 6 things because there's fluorines. And what does 6 things mean? What type of geometry? And what does that type of geometry mean for the hybridization? So how many think it's A, sp2? How many think sp3? How many think sp3d? How many think sp3d2? Okay, good. The class is going for D. That's right. So it's 6 things octahedral means sp3d2. And so what? Why do you care? Because there's I think there's a question on the final like this. You'll get a molecule, something like you'll get some series of molecules, and so it's like what's the hybridization for the carbon atom in 1? It's sp2, because there's 2 things. It's a linear molecule. What's the hybridization in carbon 2? It's sp2, because it's planar. And what about carbon number 3? It's sp3, because it's tetrahedral. So that's the kind of questions that you'd be responsible for.
Wouldn't number 1 be SP?
SP, yeah, did I say sp2? I'm sorry, sp, linear, sp. 2 would be sp2. 3 would be sp3. Sorry if I misspoke. So here is diatomic nitrogen, the Lewis structure at least. How many pi bonds does nitrogen have? How many think there are 0 bonds? 0 pi bonds. How many think 1? How many think 2? How many think 3? So a single bond has 1 sigma bond only. A double bond has 1 sigma and 1 pi. A triple bond has 1 sigma and 2 pi. So how many sigma bonds in the triple bond in nitrogen? It's C, it's 2, because it's a triple bond. Does that make sense? Okay. And here is my picture of nitrogen. One of my better pictures, actually, I think. So you have nitrogen here. There is a sigma bond alongside it here, and then there's a pi bond. So if it's nitrogen, there's a sigma bond here, there's a pi bond here, and a pi bond here. So, and this is actually one of the places where the theories differ, the molecular orbital theory and valence bond theory. So this picture would suggest that if you looked at the electron cloud of nitrogen, if you looked at the electron cloud of nitrogen, you would think it looked like a clover, like a clover leaf. Do you ever seen those long bars of soap, like the artisan soaps at places? I don't know if they really sell them here, but if you buy artisan soap, they have these really long chunks of soap, and they can cut you a slice. So maybe you've been to a place like that, and they have different shapes of things, and sometimes they put little things inside the soap. But I see this, I think of soap. I think of a clover leaf pattern of a clover leaf prism thing of soap, and then you can kind of slice it into that. And each slice is like a clover leaf. How it really happens, so nitrogen is more like a cylinder. It doesn't form a clover leaf. It actually forms a cylinder, and each side is symmetric. There's not a lobe on the nitrogen triple bond. It's just a plain old, it's like an aluminum can, kind of, sort of. It's it's more like it's kind of more like a Tylenol shape. So the nitrogen molecule, it's going to have, to try and draw it. It's going to have, you have the atomic centers, and then you have the electron cloud, but it kind of has a base Tylenol shape, kind of like this, but then there tends to be a little bit more electron density among places. There's a little bit more around the nucleus, but then there's also some, and it's a gradient where, I mean, it's hard to draw, at least the picture in my head. There's it's got an overall electron cloud that's, I guess, more of a football shape than it, but it is kind of not, so it's kind of a football, sort of Tylenol kind of shape. And then, but the electron density is a little bit more around the nucleus. So around the nucleus, there's much more electron density. And then, but then there's a diffuse sort of electron cloud around the whole thing. So that's how it really forms. So it doesn't form the clover leaf. And the reason for that is because how things really bond is it forms molecular orbitals, which we're going to cover right now. But how are we doing so far? Questions with this? This is important to know how many pi bonds are in things. Sigma and pi bonds, difference in them. Okay. So are you doing fine? Any questions? Okay, finally you get to the truth. I've been trying to tell you the truth through the whole semester, because when I was a student, I hated it. Do you guys feel this way? Like people, I guess you're still early in your careers. What you're going to find out is you're going to take a class and say, okay, this is what's going on. You're going to take this class, like, oh, by the way, which one in the class is wrong? And then like, oh, by the way, which one in that class is wrong? And then you keep on going, and he's like, you know what the truth is? We have no idea what's going on, you know, apparently what you learn in grad school. I mean, it's partially true. We don't know what's going on, but there's a lot of things that we do know what's going on. Oh, man, how horror. So that we do know a lot of things going on. We know that salt is made of sodium chloride, for instance. And we know that we need to breathe oxygen. So it's not like we don't know anything, right? But there's a lot of stuff we don't know. But but unfortunately, as you progress through your academic career, oftentimes things are broken down to you incorrectly. And I hated that as a student, so I've always tried, even when it's above your heads, I've tried to say, like, okay, this is what it really is, but this is what it means at this level. So, okay, so this is the truth. This is finally the truth, the molecular orbital theory. So the molecular orbital theories, why the heck did all my stuff disappear? It's like half the letters disappeared. So anyways, so why do things really bond? Things bond because of the electronic and magnetic fields of electrons, and when you combine electrons with positive nuclei, they can form new orbitals. They form molecular orbitals, and if those molecular orbitals are lower energy than them being apart, then the molecule will form. So, and that's part of the story, and what we're learning now, the research right now is how do you form those molecular orbitals also depends on the environment that the atoms are in, the atoms and molecules are in. So you have to have other molecules there to stabilize certain formations. You'll never have an elimination reaction in space. So you have to have a liquid state for an elimination reaction. Sorry if I'm talking to Oscar. Certain biomolecules, the question is, where did life come from? Can we get life from space? Can there be a dust cloud? A star explodes and there's a nebula dust cloud. Can those atoms randomly form some sort of pattern and then come up with a structure like DNA or some protein? And the answer is no. The simple molecules can form, but in order for many of the really complex molecules of life, there needs to be a liquid state, or at least a lot of matter, a liquid or a liquid-like state, because the other parts will stabilize those molecules when they form. So, and that's research right now that's forthcoming. We're learning more about that. But okay, let's go back to this. For molecular orbital theory, which is the real theory, and orbitals form, and this is also an approximation of it called LCAO, or linear combination of atomic orbitals. So let's start out with hydrogen. So hydrogen has two s orbitals, and if you remember from chapter 7, I said s orbitals are always positive. the positive signs. That's going to come important later. We talk about the p orbitals. So linear combination. There's two orbitals. You can either add the orbitals or you can subtract them. So if you add the orbitals, you get a bonding orbital, and the bonding orbital is these two spherical ones form sort of like a, I mean the picture shows a Tylenol, but it's kind of more like a football kind of shape. So you have this kind of pill-shaped overlapped orbitals, and then if you subtract the two orbitals, you get a part where there's the electron density on one side and the other, and this is where we include the sign of the wave function. So like this side of the sign is positive and the other side is negative, and then there's a node in the middle. So the node means an area of 0 electron density. So there's no electron density in the middle. This one has no node, that one has a node. And this is known as a bonding orbital, and that one up there is known as a anti-bonding orbital. Let me draw this on the side. And where'd my pen go? Okay. So you have the 1s orbital, and the y-axis here is energy. Okay? And what happens is that, so back to the valence bond theory, you have two hydrogen atoms floating around, and they approach each other. And when they approach each other, what happens is these atomic orbitals, they go away. So the atomic orbitals disappear, and two molecular orbitals form. So the atomic orbitals in this, I'm trying to use the altitude as my potential energy. So the altitude of the Earth and the height of that screen, this is potential energy. So here's an atomic orbital with this much potential energy. And then these two atomic orbitals turn into two molecular orbitals. And so here's the energy levels of the atomic orbitals. Here's the molecular orbitals. So notice that the bonding one goes down and the anti-bonding one goes up in energy. So now, hydrogen has one electron each. There's two electrons, so molecular orbitals form. The two electrons then will populate here in the molecular orbital. And since this orbital here is in lower energy, it will bond, and since low energy, it will be a stable bond. So it doesn't, in many cases, the new orbital it forms is higher energy, then it won't form. And since this is the same atom, this is very symmetric. So the energy level diagram for this is very symmetric. The amount of energy here that the anti-bonding orbital is the same, the instability of that is the same as the stability of the bonding orbital. That is not always the case for heteronuclear. For different nuclei, hetero is different. So homonuclear, it's very symmetric. Homo means same. Okay, so, and here's the picture that's in the book. So they form a bonding and anti-bonding orbital, and then, I guess can you see that? Oh, you can, okay. If you see this, this sigma, so this is lowercase sigma, that means sigma, sigma bond. And then you have the sigma star. The star means the anti-bonding. So no star means bonding, star means anti-bonding. And you might also see this. This would be sigma star U, and this would be sigma G. Do you talk about this in organic? Okay. So you might also, if you're looking outside the class, you might see a sigma G or a sigma U or a pi G or a pi U or stars with that. The G means Gerade. The U means Ungerade. That's German for symmetric. So it's specifically symmetric upon inversion. So meaning if you invert the molecule, so the molecule has an inversion center right here, And if you invert it, that means that this would invert through the center to here. If it's the same sign, it's called Garada, which means symmetric. And that's important because things that are symmetric are also Raman active. That's a spectroscopy thing. And which is, I'm sorry, I'm going above and beyond the course, but there's a reason why we do these things. So it's not like we make this stuff up just to torture freshman chemistry students, right? So this is important for how light interacts with molecules. And the Ungerada, so if you look at the Ungerada, if you look at the same idea, these 2 points, and you invert them, one's positive and one's negative. It inverts through the inversion center of the molecule. It's asymmetric upon inversion, which means Ungerada, which means that light is going to interact with this molecule in a different fashion. Okay. Now, also back this. Oh, this one actually has a football shape. That's nice. Okay. So with the bonding and anti-bonding, so we have the bonding, which I already talked about, and then the anti-bonding orbital layer, Garada and Ungerada. And the last thing I'm going to talk about is the bond order. The bond order is the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So the bond order, so BO, so BO can mean something different, but BO in chemistry class means bond order. For hydrogen, there are 2 bonding electrons minus 0 bonding electrons divided by 2 equals 1. So hydrogen has a bond order of 1. Okay. Now, which I've shown here. So here's another picture. Keep on showing you different pictures. This is the same thing. And what I want you also to understand is that in this molecule, the hydrogen atom, these s orbitals go away. So when you have 2 hydrogen atoms and they come together, the s orbitals, they disappear and they form a sigma and a sigma star. So these orbitals go away. And it also tells us another way that we can break chemical bonds. So one of the ways that chemical bonds can be broken, well, we've talked about a couple different ways. Adding energy. Add energy to a molecule, it can break bonds. Photons. Photons can break bonds. The reason why we get sunburnt is because the ultraviolet photons from the sun come and they rip electrons off of the atoms on the surface of our skin, and then the damage, and that damages cells. And then, I mean, a sunburn is it's a radiation burn. It's the electrons are being ripped off of the atoms, and it causes cell damage. That's all a sunburn is. It's a radiation burn from the ultraviolet light. So light can get rid of electrons, and another way you can get rid of a bond is to add electron density to it. If there is an open anti-bonding orbital, and if you add 2 electrons to hydrogen, so if you have H2 and you add 2 electrons to it, what you will do is you will break the hydrogen bond and you'll have 2 H-1s. So 2 H-1s do not form a molecule, they break apart and form 2 hydride ions. So adding the electron density will break bonds. This is important later when we talk about acids and bases, because this is not for this semester, but for next semester. If you've heard of the different theories, there's the Bronsted-Lowry, and then there's the Lewis acid-base theory. Lewis acid-base theory says that an acid is electron acceptor and a base is electron donor. Acid-base reactions, what happens is the base gives electron density to the acid, and then, among other things, frequently a hydrogen pops off. So you can break a hydrogen-oxygen bond by adding electron density to it, and it pops off the hydrogen, forming the proton, forming like an HCl. So, or it doesn't even have to be water. So hydrochloric acid, HCl. Water is the base. It adds electron density to the HCl molecule. The hydrogen pops off, and it joins the water to form H3O+. So that's another way that bonding can be broken, is by adding electron density. Okay, so here's hydrogen. Now, what about helium? So here is helium. So can helium form a molecule? And so if we have two helium atoms come together, and the bond order for this one is 2 minus 2, so 2 bonding, here is the bonding orbital. 2 anti-bonding, here's the anti-bonding orbital, there's 2 in both. And 2 minus 2 over 2 is 0 over 2, meaning no bond order. A bond order of 0 means not stable. What if, though, what if you had this case, where you had He2 plus? So what if you have a helium atom, like somewhere really, really hot, like in the sun? So the sun is a star, it gets really hot there. And say that you have a helium atom that has one of its electrons ripped off. Can that then bond with another helium atom? And if you look at the bond order here, it is, so 2 bonding minus 1 anti-bonding is actually a half bond. And a half bond, that's a positive bond order, which would suggest that this is a stable molecule. And guess what? It turns out this is true. So we can see helium-2 plus in the sun. So this actually happened after the fact, because they weren't sure if this theory was correct, but after it was determined as correct, and among other things, they started seeing pieces of information. So, and again, this is not, so He2 plus is not a helium, another helium with s orbitals. So when you have 2 helium atoms close to each other, they do not have atomic orbitals, they have molecular orbitals. So these molecular orbitals are new energy levels. And the other thing is, so if you have molecular orbitals that have energy levels, we can do spectroscopy on them. So have you ever, like, I like space stuff, so you ever see things like, oh, there's methane on whatever, and on Titan, it's a moon of Saturn. It has an atmosphere of mostly nitrogen, but there's methane there, and there's also ethane clouds, and there's liquid ethane on the surface of Titan. And how do we know that? Like, we sent probes there. What did the probes do? Have we gone to the surface of Titan and then like taken a picture? No, what we've done is the sun is here, then the probe goes behind Titan and then looks at the light from the sun coming through the atmosphere, clouds, and also some of it bounces off of the surface, and then we analyze it. And since we know what the molecular orbitals look like for ethane and methane and nitrogen, we can then determine that there is in fact those species on that body, on that heavenly body. So we can do spectroscopy just like the atomic spectroscopy, so just like the colors of fireworks and stuff. So atomic spectroscopy, right? The fireworks colors, they come from certain elements that are in the fireworks. Just like this, we can, same thing with molecules. Of course, the math is a lot more complicated. Okay. So moving on, so we've talked about hydrogen and helium. Element number 3 is lithium. Dilithium, does dilithium form? And it turns out, so lithium has 2 valence electrons, and the 2 s orbitals can form sigma and sigma star. And dilithium, this would predict then the bond order. The bond order is 2 bonding minus 0 antibonding over 2. This is a bond order of 1. So molecular orbital theory would suggest that dilithium exists. And guess what? It does exist. If you take lithium, so you take lithium metal, and you vaporize it, you will form dilithium, or you may form, depending on the temperature, depending on the conditions, you may form dilithium diatomic molecules. And this is weird. I mean, so people didn't like this theory because look at all the things that I've just destroyed this class. We have helium reacting with helium. So now we have noble gases. Noble gases used to be called inert gases. We said noble gases tend not to react, but they do react. Even helium, the most stable element there is, can react, even and with itself. Talk about a rough partner to react with. And now we have a metal. We have metals forming covalent bonds with each other. So not forming metallic bonds, forming covalent bonds. So dilithium does exist. And I don't know, there's any Star Trek fans here? Right, you got the dilithium, like that, of course.
Dilithium chamber.
The dilithium chamber, yeah. It wouldn't be a solid. So sorry to destroy you. Dilithium would not be a solid. It would only be a gas. So we've seen dilithium, but only in the gaseous states. Because the metal, lithium metal, is more stable for the solid state or the liquid state. So once it condensed down, it would just form the metallic bond. So again, goes back to stability. And now what about beryllium? Beryllium has 2 valence electrons each. So there's 4 electrons. They would populate as such. The bond order is 2 bonding minus 2 antibonding over 2, or 0. So diberyllium, unfortunately, does not exist. So it's unstable. But let's see, I'll jump ahead. Let's see if you're following this. So, which one of these has the highest bond order? I should say. So the bond order is a number of the bonding electrons minus the number of anti-bonding electrons divided by 2. So which one of these species has the highest bond order? And it's not going to be beryllium 2, right? Because we just determined it was 0. How many think it's B plus 1? How many think it's C plus 2? How many think it's D plus 3? Okay. So let's start with, here is diberyllium. The bond order is 2 bonding minus 2 antibonding divided by 2. The bond order of that is 0. Beryllium plus, we have 2 bonding minus 1 antibonding divided by 2. That's a half. Beryllium 2 plus 2, we have 2 bonding minus 0 antibonding divided by 2. So 2 over 2 is 1. Beryllium plus 3 is 1 bonding minus 0 antibonding divided by 2. That's plus 1/2. So it's C. It's that one there. So this tells you something about electrons. So ripping electrons out of things might actually strengthen chemical bonds. And adding electrons, it depends on the circumstance. So in acids and bases, for hydrogen attached to an oxygen, if you add electron density to it, it's going to weaken the bond. It's going to break the bond. In some cases, adding electron density could strengthen a bond. It really just depends on what the molecular orbital is like. So it's a contextual argument. Sometimes ripping electrons off weakens a bond, sometimes it strengthens a bond. It just depends. Okay, so let's talk about p orbitals. How are we doing so far? Questions? Yes?
How did you figure out how many antibodies?
For this? Zoom out. The bonding, the antibonding has a star, and the bonding does not. So this is an antibond, and this is a bond. Okay, and so let's start with beryllium 2. Beryllium 2, and beryllium. Beryllium is here. It has 2 valence, 2 outer electrons. Okay, so beryllium-2 has 4 electrons. And so 4 electrons is like this. What's that?
It's pretty well lit.
Oh, jeez. Thank you. Okay. So beryllium, 2 beryllium atoms have 4 electrons. And the way you populate just like atomic orbitals, so the vertical axis of the paper is potential energy. So, oops. This sigma bond is lower energy than sigma star. So you populate 1, 2, 3, 4 like that. Right? Start with the lowest energy, then go higher. So now from this, you count then, there's 2 in the sigma, the bonding orbital, and then 2 in the antibond. So if you have 3 electrons to add, you would go 1, 2, 3, like that. So start with the lowest and then go to the highest. Is that answering your question? What is this? That's an electron. Yeah, spin up, spin down. Right. So remember when we were doing the quantum numbers, chapter 7, chapter 8. I think it was more chapter 8. So like.
It's 8.5.
Like here, can you see that with lithium? You have like the 1s2, 2s1, and then you have the 2 electrons, 1 spin up, 1 spin down, the 2s. We say spin up because we're very positive in chemistry. We're not negative folks. We like things being positive, right? And then when you have a degenerate orbitals, so same energy orbitals, they align one at a time with parallel spins. Remember that? That's Hund's rule. You don't remember that? Okay.
So I was just reading that the transition metals move opposite way.
That's
Something else.
something, yeah. That's from the Zeeman effect. Okay. So if you recall from chapter 8, electrons populate, this is called the Aufbau, the building up principle in German. The Aufbau of building up, so this is probably a better diagram for that. Oh, where'd that diagram go? Did I get past it? Oh, here it is. Do you remember this one? Oh, you missed this day? Yeah. So this is known as the Aufbau, or building up principle in German. So this is hydrogen, this is helium, this is lithium, beryllium. So boron, then carbon does not go like this. It goes like this. So that's called Hund's rule, Hunds rule. Sometimes called the bus seat rule, because if you're on the bus and a stranger comes on the bus, you don't want the stranger to sit next to you. You want the stranger to take the open seat behind you. So that's nitrogen. Now oxygen, it pairs up. Fluorine, neon, sodium, magnesium, aluminum, silicon, just keep on going. Phosphorus, sulfur, chlorine, argon, that kind of thing. So and something to note, the 4s orbital is lower energy than the 3d. So the 4s gets populated first, and then the transition metals populate as such. Okay. So, but I know I'm taking a lot of time with this, and it's just because we also have the final going up, and there's lots of time left. So I'm also using this as an opportunity to review. Does that make sense? Does anybody have any questions with the stuff here with the periodic trends and the orbital diagrams? Yep. So, but using the same concept then with the molecular orbitals is that they're going to fill with the low energy first, and then they're going to pair up this way as the spin up, spin down. The spin up just means plus 1/2, spin down minus 1/2, and that's the last quantum number. So right, we have the N, the principal, the L, the angular momentum, M sub L, the magnetic moments, and then the last one was the spin. Electrons are fermions, so they have the plus 1/2, minus 1/2. They're also fermions, so that means that the Pauli exclusion principle holds, which means that no two electrons in the same atom can have the same set of quantum numbers. So electrons are still fermions in molecules, so they can only be plus 1/2 or minus 1/2, and they're still going to have the different quantum numbers in the molecular orbitals, but they're going to form new ones from the atomic orbitals, and as such have different angular momentum and magnetic fields associated with them. So that's the complicated stuff that we're skipping, or which you will learn later on if you take more chemistry classes. So is this helping, or okay? Other questions? Okay, but let me break it down to what you need to know now. You need to look at this picture, and you have to be able to count 1, 2, 3, 4, and then notice that the star means anti-bonding, that the not star means bonding, and you have to be able to count those, and then apply to the bond order equation there, the number of bonding, in this case, 2 bonding minus 2 anti-bonding divided by 2, and the quantity 2 minus 2 over 0. 2 minus 2 is 0. 0 halves, that means bond order of 0, means it's not stable. That's what you need to know right now. Are you good with that? Okay. And actually, that level of complexity is where this course ends for the final. So if you want to shut off your brain for the rest of the class, but this is a series of classes, so I do have to teach some more material. But the final does not go higher than the bond order of a series of s orbitals. It doesn't go into the peaks.
Yeah, that's what I was going to ask. Like, what would happen with another electron there?
Well, I've got a story for you. So the things that are not on the exam that we're going to cover bonding schemes between p orbitals, atomic orbitals that form, or molecular orbitals that form by p orbitals, and heteronuclear. So heteronuclear means different nuclei, and also polyatomic. So right now we've been talking about diatomics, 2 atoms. So polyatomic, what do you do like for ozone? That's 3 oxygens, or something like that. So that's the orbital scheme becomes more complicated when you have 3 atoms rather than 2, or more than 2, I should say. So more than 2 is not on the exam. P orbitals are not on the exam, and heteronuclear, different nuclei is not on the exam. So, like I said, we are done for the material for now. But I'm still going to go on and teach. So I'm just telling you guys as students, so you know where you want to know what's testable and what's not. This stuff, which I'm going to talk about now, is not testable. So, okay. So, what about for p orbitals? And p are different because they have the orbitals themselves have positive and negative signs. So you can go. I know you're sneaking out. That's fine. So they can add, and the blue here is positive and the red is negative. That's the sign of the wave function. So do you remember we talked about wave functions? And this is the blue is a positive wave function. Red is a negative negative sign on the wave function. So we have the bonding orbital, and for destructive interference, so constructive interference. Sometimes bonding is known as constructive interference, and anti-bonding is destructive interference. In this case here, you have you have a node in the center, and then you have not much overlap between in the electron density between the atoms. So, and this is an orbital. So I mean, the p orbitals go away, and the bonding orbitals appear, and the electrons then populate in these orbitals. So it no longer has this shape; it has the shape of that on the right. And p can also have this stuff here. It can have the pi bonds. So, and here I'll just zoom on this so it's easier to see. So, for the pi bond, for bonding orbital, so they would overlap here and form this, and if they destructively interfere, you get this shape here, where you get the lobes pointing away from each other and opposite sides. And what's interesting about this, so remember the s orbital with the symmetry, a sigma bond, the symmetry is with the bonding orbital, so the Gerada Ungerada. The symmetry for a pi bond is in the anti-bonding orbital. So if it inverts along the inversion center, the anti-bonding one is the one that's symmetric. So we can, this orbital responds to light much more similarly to a bonding orbital sigma does. So that's for future classes. And this is, so yeah, the pi bond is the Ungerada and the anti-bonding is the Gerada. Yeah, chemistry majors used to have to take German. I don't know German. I know Guten Tag and Dankeschön, that kind of stuff, and like Einstein, Deistein, like 1 beer, 2 beers. I got that down. But that you ever heard German? German sounds angry. I was in Austria. I felt like everyone's yelling at me. And Oktoberfest, that's a whole other story. It's fun. But okay, so we also have p orbitals alongside the other axis as well. So this is with the plane of the paper, and then this is into the third dimension there. And here is the diagram here for the different for the diatomics in the second period. So we've already covered lithium and beryllium. They only have sigma bonding. Now, when we go to boron, carbon, nitrogen, oxygen, fluorine, neon, now there is pi bonding. And what's interesting about this is that the pi bond for the 2p is lower energy than the sigma bond. And remember I told you that generally speaking, sigma bonds are stronger, but in some cases the pi bond is stronger. This is one of those cases where the pi bond is stronger. And how would you know this? There's no reason why you would have to know this. Why does this happen? If two boron atoms come together and the electronic field of the electrons and the nuclei interact, it turns out that the pi bond with this symmetry is lower energy than the sigma bond. But when oxygen, fluorine, and neon interact, it turns out the sigma bond is low energy. It's if you do the math, you find out that it works out. But this is where chemistry is an observational science. So we're reporting back to you what we see and the characteristics that form. It's not like I didn't invent this. This is not meant to confuse students. This is meant just because this is the observable world, and this is what we've observed, and I'm just reporting it back to you. So. And this is probably, we're almost running out of time. This is a good place to end up, but I will tell you, the last thing though is, if you look at This is the valence band theory for the oxygen, diatomic oxygen. This would indicate that oxygen has everything paired up. And here is molecular orbital theory. Oxygen would suggest there's unpaired electrons in the anti-bonding orbital. And that means oxygen gas should respond, is then paramagnetic, should respond to a magnetic field. This one would suggest, the other theory would suggest diamagnetic. And because of the fact that oxygen does react to a magnetic field, is the reason why molecular orbital theory was considered valid. And then band theory and VSEPR was considered invalid. It was this experiment here that explained that. So, and this was a big deal in the 1970s. You know, not so much a big deal now, but at least a big deal among the chemistry circle. Just like string theory and quantum is right now for the physics folks. But anyways, we will pick up here next class and then go over some of the finer points of this theory because I have to finish the material even though it's not on your final. But then we will have some other activities to do in class, so it'll still be worthwhile to come on Monday. So anyways, happy Thanksgiving, and I will catch you later. Anybody do anything cool for Thanksgiving? I'm staying here. I might go to a pig roast.
Oh, what's that?
The friend's doing it.
Oh, cool. That's a good one.
Yeah.
Through the mouth, through the pit.
I don't think. I think he's just using a grill. I think he probably bought it at the store. He's probably not buying an actual pig.
Yeah.
It's like, I want my pig.
I've seen that though.
Oh yeah, that's awesome. Oh, like an emu?
Yeah.